Hello everybody.
So today we'll be going over the escape velocity and how to derive it. So let's just get right into it.
So let's say you are on this planet and it has a radius r and you have your rocket ship right here and you want to escape its gravitational field. So in order to do so, you need to travel an infinite distance away, as stated here. So the question is now, what's the minimum velocity? So we're going to call this minimum velocity our escape velocity, which is going to be v sub e. And if you know the velocity you want, you can easily find the kinetic energy you have. So we have ke is equal to 1/2 mv sub e squared. And this is our kinetic energy at the beginning of the trip. So let's put that to the side for now. Now remember, we also have the force of gravity between you and the planet, obviously, and this is going to be given by big G, big M, little m over d, which is your distance between each other. So remember, the work done by a force is equal to the force times the distance that the force was exerted over. So that's just given by our work formula, which is work equals F times distance, or displacement, which is x, right? So if you just plot this, you're going to get that work is actually equal to the area under the curve. And conveniently, since this is a force versus position graph, we actually have a force versus position graph. And sorry, this should be d squared. So if we graph this, it's going to look like this. And the total work done by gravity is going to be equal to the integral from the starting radius, because that's the starting distance, all the way up to infinity, because that's the ending distance. So this work done by gravity can be written as a simple integral expression, which is r to infinity fg dd, like this. So we can actually expand this to get integral of r to infinity of big G, big M, little m over d squared dd, like this. And this is where the integral calculus comes in, because we want to compute this integral, right? Because we want to know the total work that the force of gravity does, because we want our kinetic energy to match this. If our kinetic energy matches the work exerted by gravity in the opposite direction, then we will just barely have enough kinetic energy to make it to infinity and end with zero ending velocity. So basically, we want this work done by gravity to equal our kinetic energy. So for this to work out, we need to calculate this. And this is pretty simple to do. So you're going to grab this top portion, which is a constant, and you're going to basically ignore it while we're calculating this integral. So we're going to get r to infinity of g m m times d to the negative 2 dd. And this is a very simple reverse power rule integral. Remember, these are constants, so this is going to give g m m over d evaluated at the radius and infinity. And this is just going to give g m m over infinity, and I forgot a minus sign, remember, the negative carries, so that's a minus negative g m m over r, like such. And as this goes to infinity, this whole value goes to 0. So we're going to get g m m over r is equal to the work done by gravity, which remember is also equal to our total kinetic energy at the beginning, which is 1/2 m v sub e squared. Now here we can easily solve for v sub e. So v sub e is going to be equal to the square root, these masses will cancel out, 2 times big G times the mass of the planet over r. And this is our final escape velocity. And remember, I'm just going to write this out. This is mass of planet. And this is radius of planet. So, from here, this is all you really need to know for escape velocity. I hope you enjoyed this explanation, and I'll see you guys next time.